Black holes. Simple concept, right? Mass so dense that gravity becomes inescapable. Light goes in, light doesn't come out. End of story. But ask yourself this. If a black hole only consumes, never releases, then its mass can only grow. It can only get bigger. It can only become more. So why did Stephen Hawking calculate exactly how long it takes for a black hole to die? You can't answer that, can you? Neither could anyone else before 1974, because what we call the event horizon isn't what you think it is. It's not a wall, it's not a surface. It's a seething cauldron of quantum activity, and it's bleeding energy into space. The things you were told could never escape, they're escaping right now, slowly, imperceptibly, but inevitably. Black holes aren't eternal. They're just patient. Every single one is dying. Let me show you how. Black holes. Simple concept, right? Mass so dense that gravity becomes inescapable. Light goes in, light doesn't come out. End of story. But ask yourself this. If a black hole only consumes, never releases, then its mass can only grow. It can only get bigger. It can only become more. So why did Stephen Hawking calculate exactly how long it takes for a black hole to die? You can't answer that, can you? Neither could anyone else before 1974, because what we call the event horizon isn't what you think it is. It's not a wall, it's not a surface. It's a seething cauldron of quantum activity, and it's bleeding energy into space. The things you were told could never escape, they're escaping right now, slowly, imperceptibly, but inevitably. Black holes aren't eternal, they're just patient. Every single one is dying. Let me show you how. The standard story you learned is this. Black holes are cosmic vacuum cleaners, inescapable gravity wells, the end of the line for anything unlucky enough to cross the event horizon. That's not wrong exactly, but it's catastrophically incomplete, because that description treats black holes as simple objects, static, unchanging, frozen in time. But here's the thing that should bother you. Nothing else in the universe works that way. Stars burn out. Galaxies disperse, protons may eventually decay. The universe runs on change, on thermodynamics, on the relentless flow of energy from hot to cold. Why would black holes be exempt? The answer is, they're not. Hawking discovered something hiding at the edge of darkness, something that connects quantum mechanics to gravity in ways nobody expected. Something that means the most permanent-looking objects in the cosmos are slowly, inexorably dissolving. And when you understand how, you realize we've been thinking about black holes, about space itself, completely backwards. Let me start with something you already know, something simple, and then I'll show you where it breaks. Start with something you already accept. Empty space isn't empty. You've probably heard this. Quantum mechanics tells us that even in a perfect vacuum, no matter, no light, no anything, the universe is buzzing with activity. Virtual particles flicker in and out of existence. Pairs of particles and antiparticles pop into being, exist for an impossibly brief moment, then annihilate each other and vanish. This isn't speculation. This is measured. The Casimir effect, discovered in 1948, proves it. Put two metal plates close enough together in a vacuum, and they'll be pushed toward each other by the pressure of these virtual particles. We've tested this to extraordinary precision. Empty space is a seething quantum foam. Now here's the thing. This happens everywhere, all the time. Right now, in the space between your eyes and this screen, particle pairs are appearing and disappearing faster than you can imagine. Normally, you'd never notice. The particles appear, annihilate each other, and the universe's books stay balanced. No energy gained, no energy lost, just a constant quantum shimmer beneath reality. But what happens when you do this near a black hole? Stop and think about that for a second. Picture the event horizon, that invisible boundary where escape velocity exceeds the speed of light. Just outside it, space is twisted almost to breaking. Gravity is pulling at everything with unimaginable force. And in that warped space, particle pairs are still appearing, popping into existence right at the edge of no return. Now imagine this. A particle pair appears. One particle forms just outside the horizon. Its partner forms just inside. The one inside falls in. It has no choice. Nothing inside the horizon can move outward, but the one outside, it's on the survivable side of the boundary, and with its partner gone, swallowed by the black hole, it has nothing to annihilate with. It escapes. A particle just left a black hole, not from inside technically, but from the black hole's perspective. Something just happened that shouldn't be possible. Energy just left, mass just decreased. The black hole just got lighter. This is Hawking radiation, discovered on paper in 1974, and it changes everything we thought we knew about black holes. But that's just the surface, because if particles are escaping, that means energy is leaving. And if energy is leaving, let's be precise about what's happening. A black hole isn't sitting there passively, it's radiating, constantly. Particles are streaming away from its event horizon in a faint, ghostly glow. Hawking calculated the exact spectrum of this radiation. It matches something called black body radiation, the same kind of glow you get from any hot object. A heated iron bar, the filament in a light bulb, the sun, the same kind of glow. That means black holes have temperature. Let that sink in. The things we thought were absolute darkness, perfect cold, total absence, they're warm, they're glowing. They're radiating heat into the universe just like everything else that has temperature. A stellar black hole, one formed from a collapsed star, maybe 10 times the mass of our sun, has a temperature of about 0.000000006 Kelvin, 6 billionths of a degree above absolute zero. That's cold, unimaginably cold, colder than the cosmic microwave background radiation that fills all of space. But it's not zero, and anything with temperature above zero radiates energy. That's not a suggestion. That's the law. Thermodynamics doesn't make exceptions. Not for stars, not for planets, not for black holes. So black holes radiate. But wait, if energy is leaving, where is it coming from? Here's where it gets uncomfortable. Einstein told us something in 1905. Energy and mass are the same thing. E equals mc squared. Energy equals mass times the speed of light squared. That equation works in both directions. If a black hole is radiating energy, it's losing mass. There's nowhere else for the energy to come from. The black hole is spending itself. Think about what that means. Every photon that escapes, every particle that radiates away, makes the black hole slightly lighter, slightly smaller. The event horizon shrinks, imperceptibly, but it shrinks. The black hole is evaporating. Now here's the thing that should bother you. Hawking calculated the rate of this evaporation, and he found something deeply counterintuitive. The smaller a black hole gets, the hotter it becomes. And the hotter it becomes, the faster it radiates. And the faster it radiates, the faster it shrinks. It's a runaway process. A black hole with the mass of our sun would take 10 to the power of 67 years to evaporate. That's a 1 followed by 67 zeros, longer than the current age of the universe by a factor so large it's meaningless to human intuition, but it's not infinite. A smaller black hole, say the mass of a mountain, would evaporate in about 10 billion years, still vast, still longer than the sun has existed, but reachable. And a black hole the mass of a car, it would explode in a fraction of a second. The final moments of evaporation are violent. As the black hole shrinks to nothing, it gets hotter and hotter, radiating more and more intensely until, flash, gone. Every black hole has an expiration date. We're not done. There's another layer, because if black holes have temperature, they have something else too. Temperature isn't a standalone property. In physics, temperature is connected to something deeper. Entropy, disorder, information. Anything with temperature has entropy. A cup of coffee, a star, you. Every warm object contains a certain amount of disorder, a certain number of possible arrangements of its internal parts. So if black holes have temperature, they must have entropy. This should break your brain. Think about what falls into a black hole. Stars, planets, gas clouds, information. A black hole could swallow a library containing every book ever written, every thought ever recorded, every pattern of every snowflake that ever fell. And from the outside, it would look exactly the same as a black hole that swallowed random hydrogen gas. Where did all that information go? Before Hawking, physicists assumed it was just gone, erased, destroyed. The black hole was a perfect information shredder, but that violates everything we know about physics. Quantum mechanics says information cannot be destroyed, ever. The rules of the universe are reversible. Every state can, in principle, be traced backward to its origin. Information is conserved like energy is conserved. So what happens to the information? Jacob Bekenstein, working just before Hawking, proposed something radical. The information isn't gone. It's stored, encoded somehow in the structure of the event horizon itself. He calculated the entropy of a black hole. And he found something astonishing. The entropy isn't proportional to the volume of the black hole. It's proportional to the surface area of the event horizon. Stop and think about that. Everything that falls into a black hole, three-dimensional objects with complex structure, gets encoded on a two-dimensional surface. All of it, every bit of information, painted somehow onto the boundary of the black hole. This is called the Holographic Principle, and it suggests something terrifying about the nature of reality. Maybe our three-dimensional universe is itself a projection. Maybe all the information that makes up everything, you, me, the stars, the galaxies, is actually encoded on a distant two-dimensional surface. Maybe depth is an illusion. Hawking radiation doesn't just mean black holes die. It means black holes have internal structure we can't see. It means information is preserved in ways we don't understand. It means space-time itself might have microscopic properties, quantum properties, that we're only beginning to glimpse. And here's where the real mystery begins. Because when a black hole evaporates completely, when it vanishes in that final flash of radiation, what happens to all the information it swallowed? Let's return to what you thought you knew. Black holes are eternal. They only consume. They're the universe's final endpoints. Matter goes in, nothing comes out, and that's the end of the story. Forever. You could be forgiven for believing this. It's what we taught for decades. It's intuitive. It's clean. It makes black holes simple, except it's completely wrong. Pause. The darkest objects in the universe are glowing. Let me prove it to you. Hawking didn't guess this. He didn't speculate. He calculated it. He combined quantum field theory with Einstein's general relativity, two frameworks that had never been successfully merged, and he derived an exact formula for the temperature of a black hole. Temperature equals Planck's constant times the speed of light cubed, divided by 8 pi times the gravitational constant times the mass times Boltzmann's constant. That's not poetry. That's a measurement. Precise, testable, falsifiable. And it tells us that every black hole, every single one that has ever existed or ever will exist, has a temperature above absolute zero, which means every black hole radiates, which means every black hole is losing mass, which means every black hole is dying. The numbers are exact. A black hole with the mass of the Sun, 10 to the power of 67 years to evaporate. A black hole with the mass of Earth, 10 to the power of 50 years. A black hole with the mass of the Great Pyramid, about 10 to the power of 40 years. The numbers are incomprehensibly large, but they're not infinite. Think about what this means. The supermassive black hole at the center of our galaxy, Sagittarius, a star 4 million times the mass of the Sun, will evaporate. It will take something like 10 to the power of 87 years. That's so long that the current age of the universe, 13.8 billion years, is essentially a rounding error, but it will happen. The universe is patient, and the universe wins. Every black hole that has ever formed, from the first stellar collapses billions of years ago to the monsters at the hearts of galaxies, is temporary. They're all melting, slowly, imperceptibly, but relentlessly. The most permanent structures in the cosmos are dissolving. Think about what else this means. You were told nothing escapes. Wrong. Energy escapes constantly. You were told black holes are cold. Wrong. They have temperature. You were told black holes are simple. Wrong. They have entropy, internal structure, information content. You were told black holes are the end. Wrong. They're a process, a temporary wound in space-time that slowly heals. The cosmic prisons have a release date. Here's the quotable version. The version you'll remember when you look up at the night sky. Black holes ain't so black. Hawking's own words, dry, simple, devastating. The things we thought were perfect darkness are radiating light. The things we thought would last forever are running out of time. The things we thought were final endpoints are actually just slow. This isn't speculation. This isn't philosophy. This isn't a metaphor. This is measured. This is calculated. This is the actual structure of reality. And once you see this, you realize something even stranger. Because Hawking radiation doesn't just tell us about black holes. It tells us about the fabric of the universe itself. Now here's what people miss when they learn just about Hawking radiation. They think it's a fact about black holes, an interesting quirk of extreme physics, something that happens out there far away at the edges of the universe where gravity goes insane. But Hawking radiation isn't about black holes, it's about horizons. Any horizon. The same mathematics that predicts radiation from black hole event horizons also predicts radiation from any boundary that separates an observer from information they cannot access. This is called the Unruh effect. Accelerate hard enough through empty space, no black holes anywhere nearby, and you'll measure a temperature. The vacuum will appear to glow, particles will seem to radiate from nothing. Why? Because acceleration creates a horizon, a boundary beyond which information cannot reach you, and horizons radiate. The same principle, the same mathematics, the same fundamental truth. Think about what this means. The connection between gravity, quantum mechanics, and thermodynamics isn't a quirk of black holes. It's woven into the structure of space-time itself. Wherever you create a horizon, wherever you establish a boundary that hides information, temperature appears, entropy appears, radiation appears. This is telling us something profound about the universe. Space-time has microscopic structure. We don't know what that structure is. Not yet. String theory proposes one answer, loop quantum gravity proposes another, but Hawking radiation tells us the structure exists. Something is happening at scales so small we can't probe them directly. Something that connects information, energy, gravity, and quantum mechanics in ways we're only beginning to understand. The black hole isn't special, it's just loud. It's the most extreme example of a principle that operates everywhere, all the time, at every scale. Horizons have temperature, boundaries have entropy. Information never truly disappears, it just gets encoded in ways we can't easily read. And here's the connection that should keep you up at night. The universe itself has a horizon, the cosmic event horizon, the boundary beyond which light will never reach us because space is expanding too fast. We can see about 46 billion light years in any direction. Beyond that, hidden, inaccessible, information we will never receive. If horizons have temperature, does the universe's horizon radiate? Yes, it does. The cosmic horizon has a temperature of about 10 to the power of minus 30 Kelvin. Almost nothing, but not nothing. The same physics that makes black holes glow makes the entire observable universe glow, faintly, imperceptibly, but measurably, in principle. You're not separate from this. You're inside a horizon right now. Multiple horizons, actually. The cosmic horizon. The horizons created by your own acceleration through spacetime. The horizons that form every time information becomes inaccessible to you. Hawking didn't just discover something about black holes. He discovered something about the architecture of reality. Information is physical. Entropy is geometric. Temperature is relational. And the boundaries we draw around what we can and cannot know aren't just abstractions. They're thermodynamic systems with real physical properties. The universe writes everything in a language of horizons and information. We're only beginning to learn to read it. So when you think about Hawking radiation now, remember, you're not just thinking about dying black holes at the edge of the cosmos. You're thinking about the deepest connection physics has ever found between knowing something and the energy required to know it. So, what is a black hole, really? Not a vacuum cleaner, not an eternal prison, not the end of anything. A black hole is a temporary structure in space-time, a region where gravity has curved space so severely that a horizon forms, a boundary of no return, and that horizon, like all horizons, has temperature, has entropy, radiates energy. The black hole is born in violence, a massive star collapsing, space-time screaming as it twists, and from the moment of its birth, it begins to die, slowly, imperceptibly, particle by particle, photon by photon, the black hole bleeds mass into the void. Given enough time, and the universe has nothing but time, every black hole evaporates. The things that swallow light are themselves swallowed by time. But understanding this isn't just about black holes. It's about what we can know, and what it costs to know it. Before Hawking, we had two physics. Quantum mechanics, governing the small, general relativity, governing the large. They didn't talk to each other. They didn't have to. Atoms didn't care about curved spacetime. Black holes didn't care about uncertainty principles. Hawking forced them together. He aimed quantum mechanics at an event horizon and calculated what happens. And what happens is radiation. What happens is temperature. What happens is a bridge between two worlds that had never touched. That bridge is still incomplete. We still don't have a full theory of quantum gravity. We still don't know exactly what happens to information when a black hole evaporates. The information paradox remains unsolved, one of the deepest open problems in physics. Hawking knew this. He was honest about it. Not only does God play dice, he said, but he sometimes throws them where they cannot be seen. The mystery isn't gone. It's deeper than we thought. But here's what we do know. In 1974, a physicist in a wheelchair, unable to write equations, unable to turn pages, working entirely in his mind, derived a formula that connected gravity to quantum mechanics to thermodynamics. He proved that black holes glow. He proved that black holes die. He proved that the most extreme objects in the universe follow the same laws as everything else. No exceptions, no special cases, no escape. The universe is consistent. The rules apply everywhere. That's not a small thing. It means the universe is comprehensible. It means the same mathematics that describes a cup of coffee cooling describes a black hole evaporating. It means we can sit here on this tiny planet and deduce truths about objects millions of light years away that we will never visit, never touch, never directly observe. Hawking looked into absolute darkness and found it glowing. He found equations where everyone else saw mystery. He found an ending where everyone else saw forever. The universe doesn't hide its secrets. It encodes them in horizons, in entropy, in the faint, patient glow of radiation escaping from from the edge of oblivion. We're learning to read those codes. That's what a black hole really is. Not an eternal prison, not perfect darkness, not the end. A temporary wound in space-time that the universe slowly heals, radiating its secrets back into the cosmos, one particle at a time. Not comfort, not simplicity, truth. If this journey into the dying light of black holes changed how you see the universe, if you'll never think of darkness the same way again, subscribe and share this with someone who still thinks black holes last forever. What other cosmic certainties do you think are hiding secrets like this? What else have we accepted without really understanding? Tell me in the comments. The universe is stranger than you think, and we're just getting started.